I'm Cassie. Welcome to Real World Science.
Real world science. Real world science.
Today, we're going to learn the science behind sound. So get your ears ready because we're going to make some noise.
Real world science. Real world science. Science in the real world.
You encounter sounds every single day, from the moment you wake up until the time you go to sleep. Think about all the thousands of sounds that you hear every day. Some sounds are awful noises, like that sound you hear when someone scratches fingernails on a chalkboard. Some of those sounds are more pleasant, like music, for instance. We know that if we strum a guitar, it makes a sound. But what exactly is sound? That's simple. Sound is energy. Here's how it works. When you strum a guitar, it causes the strings to vibrate. Vibration is a movement either back and forth or up and down. You can see the vibration if you look at the guitar strings up close as they make a sound. You can even see vibration on a snare drum. Notice how the chains move when the drum is hit. How does the sound get from the guitar or the drum to your ear? Well, in the case of the guitar, the vibration of the guitar string disturbs the surrounding air molecules, and the sound travels through the air to your ear in the form of a wave. Those waves travel into your ear, where they vibrate your eardrum, which is kind of like the drum we saw earlier. Nerves carry the vibration to the brain, and the brain then interprets the vibration and recognizes that the sound you are hearing is a guitar. The same thing happens for any sound you hear, whether it's a musical instrument, your mom calling you to dinner,
Cassie, dinner.
or that awful sound of fingernails on a chalkboard. The sound waves travel to your ear, and your brain interprets the sound. Pretty neat, huh? To better understand exactly what is happening when you hear a sound, let's take a closer look at sound waves. First, you should know that sound waves can travel through any medium. A medium is any solid, like the ground, or gas, like the air, or liquid, like water. In fact, sound must use a medium in order to travel. So in outer space, you can't hear anything because there is no air, no medium that the sound waves can travel through. Sound waves transfer energy. You can see how a wave is formed by looking at this fishing bobber as it hits the water. Notice that when the bobber hits the water is disturbed, causing energy, waves, to go out from the source of the disturbance, in this case the bobber. Sound works the same way. A sound creates a disturbance and pushes molecules away from it in the form of a wave. If you could see a sound wave, it would look something like this. A sound wave is a special type of wave called a longitudinal wave. It moves back and forth like a spring. Where the molecules are squeezed together, it's called a compression. Where the molecules are stretched apart is a rarefaction. A series of compressions and rarefactions that represent the transfer of energy is a longitudinal wave. Let's review what we have learned so far. We know that sound is energy, and it starts as a vibration. Sound travels in the form of waves and needs a medium to travel. Sound waves are a special type of wave, a series of compressions and rarefactions called a longitudinal wave. Now that you know some of the basics of sound, let's talk a little bit more about longitudinal waves. The first picture of a sound wave that we saw looked like this, a series of compressions and rarefactions represented by molecules. But sound waves can also be represented like this. Notice how the wave goes up and down, with high points called crests and low points called troughs. The crests that you see represent compressions, and the troughs, rarefactions. Now, we can measure sound in several different ways by analyzing the properties of this longitudinal wave. The first property of sound that we are going to discuss is amplitude. Amplitude describes how loud or soft a sound is. We can measure amplitude by measuring the height of a sound wave, the distance between the center of the wave and the crest or the trough. A loud sound might look like this, and a softer sound might look like this. The unit of measurement used for amplitude is the decibel, shown as the symbol dB. It's important to note that when sound is over 120 decibels, it can be dangerous and your ears know it. At that point, the sensation of sound is replaced by a sensation of pain. That's one reason why parents tell you to turn down your music. They don't want you to hurt your ears.
Tyrone, please turn down the music.
Another property of sound is wavelength. This is the measurement of the distance between two high points or two low points on a wave. Frequency is another property of sound. This is the measurement of the number of waves that pass a certain point in a given time period. Frequency is measured in units called hertz, shown as the symbol Hz. 1 unit of frequency is equal to 1 cycle per second. The more energy a sound has, the higher its frequency. Now, frequency determines what is called the pitch of a sound, how high or low a sound is. A flute, for instance, has a higher frequency and higher pitch than, say, a tuba, which has a lower frequency and thus a lower pitch. Did you know that dogs can hear sounds with much higher frequencies than humans can? Humans hear frequencies that range between 20 and 20,000 hertz. And dogs can hear sounds with frequencies of up to 35,000 hertz. That's why when you blow on a dog whistle, people can't hear it. Only dogs can. And if you think that's a lot, imagine how amazing bats must be. Some bat species can hear sounds with frequencies up to 100,000 hertz. Sound is especially important to bats because it helps them to navigate. Bats don't have the greatest eyesight, so they rely on their hearing to navigate by sending out sounds and listening to the echo. An echo is the sound reflecting or bouncing from an object. The process of using echoes to locate objects is called echolocation. By using echolocation, bats can tell how far away objects are and what the objects are, whether it's fruit, a tree, or another bat. Bats aren't the only ones who use echolocation. Other animals use it too, even people, especially on submarines and ships to detect objects in the water. People like oceanographers, scientists who study the ocean, use a special kind of echolocation device called sonar, which stands for Sound Navigation and Ranging. The sonar device sends out a signal. When the signal hits an object, it echoes or bounces back to the source. By knowing the speed of sound, scientists can calculate how far away an object is by measuring how long it takes for the sound to bounce back from the object. Before we go any further, let's take a moment to review some of the information we have learned. We learned 3 different properties of sound: amplitude, wavelength, and frequency. We learned that sounds louder than 120 decibels can hurt human ears. And although humans can't hear sounds with frequencies of 100,000 hertz, those sounds come in handy to animals like bats that use echolocation to navigate. And we learned that humans can use echolocation too, in the form of sonar. Remember we discussed that sound needs to pass through a medium in order to travel? Well, it's interesting to note that each type of medium will affect how fast sound can travel. The rate at which sound travels through the air is approximately 340 meters per second at sea level. That's over 760 miles per hour. The speed of sound traveling in air is also referred to as Mach 1. So, When you hear people in movies or on TV talk about reaching Mach 1 or Mach 2 in a jet plane, what they are really doing is comparing the aircraft speed to the speed of sound. Any object that travels faster than the speed of sound is called supersonic. Now, I said that the speed of sound can change depending on what type of matter it travels through. Well, if you take sound into water, it travels faster than it does in air, and sound travels even faster in steel. Why is that? Well, let's go back and take another look at the first image of a sound wave that I showed you, which was made up of molecules. Remember how we said that sound is energy, and that when sound travels, it's the transfer of energy. When sound travels, the initial energy created from the sound is bounced from molecule to molecule and vibrates outward from the sound source. If we watch a demonstration of sound traveling through air, we notice that it takes a while for the molecules to bounce against each other and transfer the energy through the medium. The quality of a medium that describes how quickly molecules bounce against each other is known as elasticity. Now, if we look at another graphic demonstration where molecules are packed together really closely, you can see that the molecules bounce off each other much faster, causing the energy to move more quickly. That's why sound travels faster in steel than in air or water. Solids are denser than liquids or gases. Density is just a way to describe how closely molecules are packed inside a medium. There's one other factor we need to mention that has an effect on how fast sound travels, and that's temperature. The colder a medium gets, the slower sound will travel through it. That's because the colder molecules get, the slower they move. And if the molecules can't bounce off each other as quickly, sound won't travel as fast. Let's review properties of matter that affect how fast sound travels. Density describes how closely molecules are packed in a medium. The greater the density of an object, the greater the elasticity of the medium, which helps sound to travel much faster. And the colder a medium gets, the slower sound will travel. That's because temperature affects how fast molecules can move and transfer energy. So, what can you do with all this fascinating knowledge of sound? Well, maybe someday you'll become a scientist who uses sonar to study the ocean and marine life. Or you might join a rock band and become a famous musician or singer. But for now, you can hum along with your favorite songs and enjoy the many different sounds you hear in the real world.